We now define probably the most important type of first order differential equation, and they're called linear differential equations. And it's not surprising that the word linear comes up again after all that we've done in terms of working with linear algebra. Now we get to look at what a linear first order differential equation is, and then we'll discuss how to solve them. Right. Now, a first order, so a first order DE is said to be linear, right? If it is expressible in the form. So what do they look like? Well, we would like to have the dy dx as a single term, and then there could be another term that has y, but that term could be multiplied by a function of the independent variable. So p of x is what we usually call it, and then times y, and then is equal to, and then we could have another function, also a function of the independent variable. So this is the standard form of a first order linear differential equation, right? So kind of look at that. Looking at this equation, what can we take away? Well, we can see that the dy dx and y, so the dependent variable and its derivative, again, can only be raised to the power 1, right? But it looks like they could have coefficients that are functions of the independent variable. So they don't have to be multiplied just by constants, but you could have a function of x here, you could have a function of x here, and you're allowed to add these two terms together, right? So here's a specific example. So dy dx plus x squared y is equal to the sine of e to the x. This is considered linear, right? So even though you see like an x squared, and even though you see a sine, and even though you see an e to the x, these functions only involve the independent variable x. As long as you don't have functions of y, like y squared or e to the y or the sine of y, then you're fine. So in other words, this coefficient, these are allowed to be pretty much any function, but they can only involve the independent variable. So allowed to be any function of the independent variable. Right? But as far as the derivative and the dependent variable, right? So basically the functions that the function that we're trying to solve for, the y and its derivative, can only be raised to a power 1, and they can only be multiplied by functions of the independent variable. If those two things are satisfied, then the differential equation is said to be linear. So this one, right, let's write it down, is linear. But if I make one little change and put the 2 as an exponent of the y, then it changes the classification and it's no longer linear. So if I have dy dx plus x times y squared, and that's equal to the sine of e to the x, if I make that just that one change, this one is now nonlinear. And this is because the dependent variable is now being squared, right? So here we're not allowed to have any other function of the dependent variable or its derivative, right? So here the dependent variable is being squared. And that's why it's so important to be able to identify, well, what is your dependent variable? What is your independent variable? Because if you don't have those clearly understood, then your classification um, might be incorrect. And then you might end up trying to use a method that doesn't apply, right? Just to kind of emphasize that point, if I wrote down now dx dy plus x squared y equals the sine of e to the x, then this is now non-linear. Right? This is also non-linear because now, having my derivative written in this form, it is assumed that x is a function of y, and here I have x being squared. So this now is non-linear as well. Right? So it all depends on what role your variables are playing, right? And the thing with the differential equations is that you have to consider the form of your derivative, right? It's not just x's and y's now, but you have derivatives to consider. All right. So before we talk about the actual method of solution, I do want to mention a very important theorem. Now, up here, I said that, the P and the Q are allowed to be any function of the independent variable. And in principle, that is true. But if we actually want to find a solution, right, we can't just have any old function. These coefficients, the p of x and the q of x, they have to satisfy certain conditions, right? Now, at this level of differential equations, the condition that we're going to use is continuity because it's relatively easy to check, and that's a concept that's been talked about since your first semester of calculus. So here is an important theorem. And what it will guarantee for us is when will these linear equations have a unique solution, right? So this is a theorem, and it's called the existence and uniqueness theorem. Oh, uniqueness theorem. So it tells you under what condition will we be able to, or let me put it this way, under what condition are we guaranteed that the differential equation will have a solution and that it will have only one solution. All right? So if p of x and q of x are continuous on some interval containing the x value x equals x0, then let's write it down. So here is again the general linear first order differential equation. So dy dx times p of x times y is equal to q of x. So if this is our differential equation and we have an initial condition that looks like this, y of x0 is equal to y sub 0. So this is the initial condition. So the theorem is saying if our two functions p and q are continuous on some interval that contains the initial x value, then this initial value problem is guaranteed to have a unique solution. So then the initial value problem is guaranteed to have a unique solution on that interval. So there is a solution and there's only one, right? So guaranteed to have a unique solution on that interval, same interval, on that interval, right? And that interval is called the interval of existence, right? So this interval is called the interval of existence. Right? So it's always important, when we're solving any type of problem to know, is there some kind of guarantee that we have in terms of, yes, there is a solution and now let's work towards finding it. Because you don't want to try to solve something that doesn't have a solution, right? Something that's not solvable. But this theorem pretty much gives us a guarantee. As long as P and Q are continuous on some interval, right, containing the whatever x value is being used in my initial condition, then the differential equation is guaranteed to have just one solution that passes through that particular point. All right? Let's do an example that sort of illustrates this and how we can utilize this theorem in different ways. Right? So let's say we have the differential equation, let's say x plus 1 times dy dx minus 2y is equal to x cubed, right? Now, this one is a linear differential equation, but it's not in the standard form yet. To put it in the standard form, right, I would have to go through and divide everything by this x plus 1. So I'd like to have, well, not like to, but by definition, I would need to have a leading coefficient of 1, right? And we've seen that in previous work. Now we're seeing it in the context of differential equations. So if I divide through by the quantity x plus 1, then I have three terms that I have to divide. This term, and then the term on the right side of the equation. So if I divide through by x plus 1, I will have dy dx, and then minus 2 over x plus 1 times y, and then that's equal to x cubed over x plus 1, right? So now this is in the standard form of a linear differential equation, and in terms of P and Q, P is the negative 2 over x plus 1. So this is P of x, and then this is Q of x. Right? So if we, for instance, now let's say we wanted to figure out what is the largest interval over which this differential equation could have a unique solution, right? So if we're not given an initial condition, but all we're given is the differential equation, we would have to determine the largest intervals over which both of these two functions are continuous, right? Well, going back to, again, let's say, your first semester of calculus, then p of x, which is equal to -2 over x plus 1, this function is continuous, right, for x not equal to -1. So it's continuous when x is not equal to -1. In other words, I can write this interval, and let's say we use our interval notation. Then it's the interval from -infinity up to -1, union with the interval from -1 to +infinity, right? And that's the same for this one too. So q of x is equal to x cubed over x plus 1. This function is also continuous when x is not equal to -1. So it has the same, I guess you could say, domain of continuity here, right? So what the theorem of existence is saying, as long as, like if I were to pick a value of x that's in either this interval or this interval, then we would be guaranteed to get a unique solution, right? So basically, this dE, this differential equation, has a unique solution passing through. And notice the y value doesn't even matter, but passing through the point x0, y0, as long as x0 is not equal to -1, right? The differential equation was guaranteed to have a unique solution, right? So provided, or let's just say for x0 not equal to -1, all right? So that's one example. Let's try another example. So let's say our differential equation is something like this. So, and let's say this one is already given to us in standard form. So let's say we have the square root of x plus 2 times y, and then on this side, let's say we have the arc sine of 2x, right? So this is our differential equation, and we can see that it is in fact linear. This is p of x, and this is q of x. Right? So again, let's see if we can figure out again what are all the possible values that an x0, right, could be, and we would still be guaranteed to have a unique solution to this, right? The theorem doesn't tell us how to solve it, it just tells us when for sure there will be a solution. All right, well, let's look at the continuity of these two functions. So p of x, which is equal to the square root of x plus 2, is continuous whenever x plus 2 is greater than or equal to 0. We can't have a negative under the square root. So this is telling me that my x now has to be greater than or equal to -2. All right? So that's the first condition. But then we also have to figure out for what values of x is this arc sine of 2x continuous. So q of x, which is equal to this function, is continuous whenever, now again, you might not have talked about or used the continuity of your inverse trig functions recently, but this function is continuous whenever the 2x is strictly between -1 and 1. Right? Essentially, that's the domain of continuity of this function. If I isolate the x, I get that x is between -1/2 and positive 1/2. And the theorem says that both of these have to be continuous. So then I have to figure out where these two intervals intersect. What values of x do they have in common, right? Well, this is saying that x has to be greater than or equal to -2. This one says that, in fact, let's put them on number lines, right? So I'm going to sketch two number lines, both going from -infinity to -infinity initially. For p of x is continuous whenever x is greater than or equal to -2. So let's say this is -2 there, and then it's everything this way, right? This is saying that q is continuous whenever x is greater than or equal to -1/2. So basically, let's say here, that's -1/2. And then up to and including +1/2. So let's say right there. So again, where these two intervals overlap, your x would have to be between -1/2 and +1/2, right? So let's write down the sentence. So this dE, this differential equation, is guaranteed to have a unique solution only one, but we're guaranteed to get one, passing through the point x0, y0, provided that x0 is somewhere between -1/2 and 1/2. So provided we have this, right? If x0 is not between -1/2 and +1/2, it's quite likely that we will have no solution. Or we might end up with multiple solutions, and those are a little bit strange in the context of differential equations. But if we want a unique solution, and if we knew how to solve this, right, and I can tell you that would be a difficult proposition to try to solve this, but if we could, and if I wanted you to, for instance, to find a particular solution, I would have to give you an x value that's somewhere between ±1/2. All right. So that's the just a little bit of theory behind these linear first order differential equations. And in the next video, what we're going to focus on now is how can we solve them, right? So not just in theory saying, oh, there has to be a solution when certain conditions are met, but how do we actually find those solutions, right? So see you then.